The most awkward conversations that I had to do was Kevin talking to Eric.
Oh, you were there.
Yeah.
He was saying that
Yeah.
he just sat down at the table and started talking about his theories, and Kevin just
I
felt
think
that
he's serious.
crazy.
He was like just talking about stuff. Yeah.
And Kevin said that it was like dark matter stuff too.
Right.
Just always funky.
Do we start, or do you know if anyone is like for sure coming? Waiting
Most
for?
of the PI people are on vacation right now.
Vaughn.
Vaughn should be here. I don't know. We can.
I think we can start.
If it's
Whatever,
recorded, we can start.
whatever Franny wants.
Yeah.
I personally don't have a preference. Whenever you're good to go.
A bunch of the PI people.
I
told
started
me-
recording already, so.
Okay, might as well start
Yeah,
then.
yeah.
All right.
I think so.
So, all right. So my goal is to talk. Okay, the past couple of weeks we've been talking about the Atiyah Singer index theorem. Will gave 2 talks on pretty much a build-up towards the theorem, a bunch of K-theory and all that stuff. Not a K-theorist, but I'll do my best to kind of continue from his point of view. Yeah, so the theorem that William managed to build up to is that if you have a closed manifold, so compact boundaryless manifold, and you have an elliptic operator, then on this manifold, then the analytic index and the topological index are equal. So just in case, the analytic index, since your operator D is elliptic, in particular it's Fredholm, so it has closed image, the kernel and co-kernel are finite dimensional, and the index is defined as the dimension of the kernel minus the co-kernel. Or the other way around, one of the two.
Yeah, so it doesn't matter if it's the other way around, or it doesn't matter, or?
Well, it has to be positive, so whichever one.
Okay.
One of them is going to be bigger than the other one, so just take whatever is positive.
Whichever one is fine.
Yeah. Once you figure that one out, it's the same formula for all. So, okay. And the main problem with this is really what is a topological index. That's a problematic thing to play with. So the way I'm going to go through this talk is kind of review the last few weeks, so kind of try to summarize it a little bit. Also, in some of the talks, William didn't go much into partial differential operators, so I'll try to kind of elaborate a bit more on those. Eventually write what the topological index is. Then a few corollaries. The reason why the index theorem came to be is because you have all these different theorems that relate some topological invariant of your space with a numerical invariant. So if you look at the few of the corollaries we're going to look at is Gauss-Bonnet theorem. You also have the Riemann-Roch theorem, and you have more that I might not talk about, but the Hirzeberd signature theorem and so on. And these all relate some numerical, so some number, some integer with a topological invariant. So we're going to talk about some of these corollaries. Then we're going to use this, which is the main use that I know of the Atiyah Singer index theorem. I've only seen the proof once using the heat kernel approach from a seminar a couple of years ago, but I never really used it beyond, I've never seen it being used beyond computing dimensions of moduli spaces. So that's what we're going to use it for, and hopefully I managed to go all the way there, because there's a bunch of things to say in every single part, so hopefully I get to there.
Oh, we have a comment though. Well, sorry, Will, 1 second. Let me just put you on speaker here. Go for it. Oh, no, you're not talking to her. Sorry, 1 second. Sorry, try now. Yes.
Okay. Yeah, so you said like the index has to be positive, but that's in contradiction to what you said about you can have the Euler characteristics that is an index and the signature can be an index. I don't think like it doesn't have to be positive. It's always the kernel minus co-kernel.
Okay, then you leave that one there.
Okay.
Oh, you're right. Yeah, no. I'm being dumb. No, you're right. Okay, thank you for the clarification. So I didn't have my formula correctly. Okay, now again for a review, analytical index, we did it, it's quite simple to describe, that's not so hard. So let's talk a little bit about the topological index. So again, how is this defined? Topological index is really the index of, you have a differential operator. What we're going to do is assign to this the symbol, the k-theoretic symbol, to this D, which is going to be something that is in K-theory with compact support, and we're going to find the topological index of that. So this will be done in the past couple of weeks, but I'm just going to elaborate a bit on the partial differential operator part of this thing. So what is a partial differential operator? Okay, so I guess first we're going to build up to what is an elliptic operator again. So let's begin with the definition of a partial elliptic operator, PDO, which I'm just going to refer to it from now on. So suppose we have a vector bundle, two vector bundles over M, and we're going to work over the complex vector bundles. So if you have this, then an operator, so a linear operator, L, which goes from the space of sections of E to the space of sections of F. Again, I'm working in the smooth category, so these are smooth vector bundles and these are smooth sections. We say that this is, let me go down. So we have this operator, and we call this to be, we're going to say this is local if the support, if let's take a section of E and evaluate it at U, the support of this is contained the support of U. So again, partial PDOs, want to think of them as kind of taking derivatives. If you have a function whose support is in a given set, then its derivative, the support of its derivative has to be contained in that given set. So outside support is going to be 0, so you want the derivative to be 0 as well outside. And this is for every U. Okay. So, okay, once you have this, we're going to define the following. I guess actually I could have omitted this definition because this is going to be a corollary of whatever I define it next. There's a couple ways to define PDOs, and I'm going to go for a more global approach. But for, suppose I have a smooth function, my manifold, we're going to define the following. The operator ADF this is going to go from the space of all operators from E to F. And it's going to give me another operator from E to F. This is going to be defined by ADF. I'm going to take an operator L. Again, this should be an operator from E to F. It's going to take a section of E, section U, and it's going to give me the following. It's going to be L of FU minus F of LU. It's for every U. Okay. So now that I have this, I'm going to define my partial differential operators of order k inductively as follows. So first off, what do I want a PDO partial differential operator of order 0 to be? It's going to be of order at most 0 between E and F. It's going to be the intersection of for all the smooth functions of kernel of adjoint F. So what I want for a partial differential operator of order 0 is pretty much to be linear. It's in the kernel, which just means I can take the F out. So I want it to be that. And now if I want to go for the other ones, I'm going to do it inductively. PDO of order at most k between E and F is going to be a linear operator between E and F, or between the sections of E and F, I want to be precise, such that if I take the adjoint of, like this adjoint F, and I evaluate it at L, I want this to be in the k minus 1, the PDO for the k minus 1 between E and F. I should probably be a bit more mindful of my space. Let me write it down here. L. I want this to be PDO for the k minus 1 E to F. And So if you want to think about this a little bit more, I want my partial differential operators to really act as kind of derivatives or derivations. So I can think of this as if I take the derivative of something, I want it to go down one order. These are going to take the derivative of a section, and I'm saying how it behaves with respect to these functions. Okay.
Are you requiring these L's to be linear or?
Yeah. So these are all linear. My operator really meant linear. Operator. Yeah. So linear over the field. Sorry.
Are they like K-linear?
Yeah. Linear over the field. Yeah. So over the complex numbers in this case. And okay, so if I talk about a general PDO, it's just a union of all of them. The union over K, PDO, K, yeah. And if I want to talk about, so these are operators of order at most K. Now if I want to talk about an operator of order K, I'm just going to take my PDOs of order K at most K and take away those of order at most K minus 1. Yeah, I'm going to take away the PDOs. Okay. So now we have partial differential operators. You have a few examples you can think about. Partial differential operators of order at most 0, like I mentioned, they're just linear operators that are linear over the smooth functions. So it would be, yeah, so you have that. If you take E and F to be the trivial bundles and M to be Rn, then these are like the tangent vectors, the d by dxi, they're going to be partial differential operators of degree 1. If you have the exterior derivative, that's a partial differential operator of degree 1 as well. It's going to take a single derivative of order 1, sorry. So it's a single derivative. And if you think of those of order greater than them, then you're taking like multiple derivatives. So locally, we can prove this from here, is that locally, if you take a charge over that trivializes M and that trivializes E and F, then locally this looks as follows. Differential operator is going to be of the form, let me write it down. So if I take this and evaluate at a section S, it's going to be locally of the form A alpha x. So it's going to be at a point x. It's going to be of the form alpha s at x. This alpha is a multi-index over K. So that's equal to K. So L is a PDO of order at most K, and that is a multi-index. So where alpha is a multi-index over the manifold, and so n is my dimension of the manifold. It's the sum of the alpha i's, and the alpha is d1 alpha 1 n. So locally we look at this form, and A sub alpha is a K by n matrix, and X is yes, rank F times rank E. Okay, so that's how does a PDO looks like locally over at most K. So you have this matrix of functions, and it's telling you how to differentiate these sections. Okay. So yeah.
I just have a question. To get this, would you also have to like assume that the first order ones are like obey some kind of Leibniz rule or something like that?
Sorry.
Wouldn't you have to like assume that like the order ones obey some Leibniz rule or something?
No, it follows from these ones.
Okay.
Yeah, the ad is going to take care of that. So the fact that you may choose them to be inductively defined like this is going to force them that you satisfy Leibniz rule.
Okay.
Yeah. You can also define them like this, and you have to have the condition of being local. So if you have an operator of sections, a linear operator between the sections, that locally looks like this, and is local, these two are equivalent.
Okay. Yes.
So yeah, it is included in the definition. Okay. Good. So here's what we have. Okay, now we can define the symbol. And for that, we're going to note the following. So actually, we're not going to note it, I'm just going to state it. But I don't even need to go into that. Let's just define the symbol again. If I have some element L, in order K differential operator, and X is an M. I guess I could just take to be at most K. We're going to define the symbol to be the following. So we're going to define sigma sub X L. This is going to be a map from the symmetric k-fold symmetric product of potential bundle tensor C into given as follows. So sigma X L of okay, I think in my definition, I might have to change my definition because the way I define it is just like this. I just define it like this. But it's going to take some cotangent vector at x, and it's going to give me following 1 over 2 factorial. I'm going to do add recursively at f k times. And I'm going to do that at L. This would be the order 0, where C is equal to df in a neighborhood of x.
Why does it do 0?
Sorry? Because you're applying k times. So this has order at most k. If I apply add f, it's going to be k minus 1, k again.
And then I can evaluate it at the point. Actually, the way you defined it, it's not obvious that these are just functions, right? So why can you evaluate the PDO at the point?
Yeah, okay. So here's what I'm saying. Okay, so these are linear operators between E and F. If I apply F a bunch of times, I'm going to have a linear operator of order 0 between E and F.
Mm-hmm.
And what I'm saying when I'm restricted to X is I'm restricted to the fibers.
Function.
Yeah. Is that good? Okay.
And just out of curiosity, what did you have beforehand, before you erased it?
Yeah, so I had it in the symmetric product of, so that requires a bit more work. So I had it with the symmetric K tensor C. The thing that happens is that here you can actually take to be, you can define a different function from that takes K different inputs, F1 to Fk, and you can show that that function actually is symmetric.
Okay.
And it's only defined, it's purely defined by evaluating at the same function everywhere.
Okay.
So I kind of omitted some steps, but more generally, it is in the symmetric case. I didn't have to go there. Okay. We're good now. So, what does this tell me? This definition tells me that actually I have the following: simply that sigma L is a section of y star E, y star F, where y is the projection. So I'm pulling back my vector bundles on M to the cotangent bundle, and my sigma, my symbol, my principal symbol, is actually a section of this bundle. Okay, so I have a couple of examples if you want to compute them, but what I'm going to say is kind of related back to what Will has talked about the past few weeks, because he did more K-theory, and this is more like an analytic thing. I defined a section and all this stuff, but Will defined the symbol to be a K-theoretic object. So So how does that work? Well, that actually comes from the fact when you restrict to elliptic operators, you manage to get an element in K-theory. So the way it works is as follows. So we can do some computations afterwards, but one last definition is L have a PDO between E and F. We say that this is elliptic if for every P M and for every non-zero cotangent vector, we have that sigma x, L, and evaluate this at sigma is going to be a map comp between these two. It's going to be EX to EF if this is an isomorphism. Okay. So what it's telling me is that outside of the zero section, I want my principal symbol to be an isomorphism. And if you recall correctly as to how we'll define the chains in K-theory with compact support, it was things that were isomorphisms outside of compact sets. A manifold is compact, so the zero section is a compact set, and I'm saying that my principal symbol is an isomorphism outside of this compact set. So it defines an element in K-theory with compact support. And there was the other thing about the cotangent bundle and the tangent bundle. It was what you said, that you just fix a metric, identify the tangent bundle with the cotangent bundle, and now you get a K-theoretic element by looking at the tangent bundles. So we're going to go into that in a little bit, but so far this was a review of what Will has talked about this last few weeks. So any questions?
Do you still need to complexify T star M there as well, because your bundles could be complex? Or
Yeah, I do think here I would have to complexify this one. For this definition, it doesn't really matter as far as I can tell, as far as I remember. Like you still have the same definition, just that you would have over real bundles, and then the results afterwards might not work. But you can still have the same, all these things still work if you restrict to the real numbers. Just that the theorems afterwards don't, or not. Exactly. Okay. So I'll keep it complexified because we want to work with complex stuff. Okay. So I think Will mentioned this briefly, or I don't remember how deep he went into it, but for a couple of the examples, having an elliptic operator is not just enough. We actually care about kind of chains of oscillators. So we're going to have to kind of expand this definition to when we have a chain of vector bundles with PDOs over them. So, okay. So I'll do this definition, then we're going to work through some examples to kind of get a feel of how it actually works. So again, definition. So when do we have an elliptic complex? It's what I'm going to define right now. If we have a complex we're going to have 0, we're going to have sections of a vector bundle E0 that goes to sections of a vector bundle E1, and so on. We're going to assume that this terminates eventually. En 0, so 1. We said this is an elliptic complex. It's an elliptic complex. If first it's I have Li composed with Li minus 1 equals to 0, it wants to be a co-chain complex, a chain complex. And the second condition is for every x in M, and for every C in T star M, it's M, away from the 0. We have an induced complex of symbols, the complex. And I'm going to have 0 into E0 x, if 1x is going to have the symbol of L0 at x with a given 1 there, be the symbol at x, L1 valued at C, and so on. En x to 0 if this is exact. Outside of the 0 section. So yeah, so this is true like this. Or you can just say that if the associated chain of symbols is exact outside of the 0 section. So this is mainly what we're going to work on, because if you think of the theorem complex, you have a chain and you have a bit more structure there. So this is what we have. Okay, also some justification why you have an induced thing here is also if you have the composition of operators, of elliptic operators, of symbols. Sorry, you have the composition of PDOs, the symbols compose, Q. And if you have the composition of elliptic operators, it's going to be elliptic as well. So you can just get an induced chain. And here you don't need ellipticity, but just general facts of life. So now let's do some examples to kind of get a feel. So let's do an easy one first. You want that, I'm sure you could all do by yourself, and then we're going to go for a harder one. But if I have my serial derivative from the 1 forms in R3 into the 2 forms in R3, we're going to identify a 1 form. So we identify if I have a 1 form u1 dx1 plus u3 dx3, I identify this with u1 u2 u3. And if I have u12 dx1 dx2 plus u23 dx2 dx3 plus u13 dx1, dx3. I'm going to identify this as well with a column vector u12, u23, and u13. Okay. So let's try to compute the symbol of D, and then we're going to do it. The same computation works for more generally. So if I have D of okay. So first, let's write it locally. How does this look as a PDO in our local form we had before? If I have D of u1 dx1 plus u2 dx2 plus u3 dx3, you can write this the usual rules you know. So this is the curl of u1, u2, u3. So you're going to have the u2 dx1 minus u1 dx2. So I'm going to go right away, just identify it as a column vector. So the u3 dx2 is the u2 dx3, and u1 u3 x1 minus x3. I think I should put this up, but just I assume all my index are correct. Now you write this as a matrix form. It's going to be 0, 1, 0, 0, 0, 0, 1, 0, 0, d1 plus minus 1, 0, 0, 0.
Maybe minus 1.
Sorry?
Shouldn't there be minus 1 in the first one? Maybe no.
No, because you have plus dx1.
Because you chose dx1, the wedge dx3, not here, so okay.
Yeah. I'm okay?
Yeah.
Okay. Yeah, actually, when I was writing it out, I was also making sure that I'm not screwing up the signs, because first use a different convention and change it in between and kind of stuff. So I want to make sure it's not then carried over here. And the last one, 0, 0, minus 1, minus 1, 0, 0, 0, xv. Okay. So from here we can see that it's a first order PDO, has order 1 on each one. And now we can compute its symbol. We actually didn't need this computation, but it's just good to have, because sometimes if you see in local form, you might wonder what these matrices are. So this is how you can compute them, the way you do like this. You really need to do that. But to compute the symbol, there's the abstract way is a bit more easy for this one. So it's order 1, so we only need to apply it once, k times for the k, but we have order 1, so we just need to apply it once. So first, the above shows that it's a PDO of order exactly 1. And if I have omega, so let's do it more generally, so let's do it there. Now for the general one, I have the external derivative for general d from k forms and m to k plus 1 forms. It's also operator PDO of order 1, and you can compute its symbol by computing the following. By definition, this is going to be should be d omega. By definition, this is d of f omega minus f d omega. Then using the product rule here, you just end up with df wedge omega. But then, what does this mean? It means that AD f d is equal to df, it's your derivative, right? So if I do more generally, so if I, again, local, this is supposed to be a linear operator between between k forms and not between two k plus 1 forms. So the way it works, so this implies that the symbol of d at x have to take a 1 form. This really is okay. So that's one example. Let's see what I want to do. Okay, so now this is for only considering D, but if we consider the whole complex, now we get a familiar result that.
Yep. There's a question from us.
Yep.
Can I ask something quick about elliptic complex definition again?
Sure.
So you have like your sequence of spaces of sections, and then you have your complex of just like E0 up to En.
Yeah.
So the second line, when you actually have the symbols going between them, should that be the pullbacks along the projection of the cotangent bundle?
Yes, you're right. Yes, it should be pullbacks. Yeah, because I think I wrote it. There you go. Like the above is a section of the palm of the pullback. So
Yeah.
it should be pullbacks.
Alright, that makes more sense.
Okay. So, okay, got that. Now let's go through the complexes. I remember when William got this complex, I was awfully confused as to why it would be worth looking at it, but I guess now that I go through this, it kind of makes sense. So let's consider the complex 0, omega 0 of m, omega 1, and so on. So my manifold is n-dimensional, so we'll go to n, 0. So again, this is an elliptic complex because if you look at the one with the symbols, what we're going to have is the following. We're going to have 0. Again, we compute the symbol for D, which is exactly this. It's going to be the 0 star. I should have pullbacks here. William showed, or I don't know if he showed it, but he mentioned that this is, no, he did show it, that this is exact. It's exact. And this is the sequence of the symbols. So we have an elliptic complex here. And this is for every x and m. And see all the way from the zero. Okay. These are a couple examples to get us familiarized with this. And we're going to go for a different one by the end when we compute moduli spaces. All right. Okay. So now I'm going to do one big leap in direction and just kind of rewrite the index theorem in terms of the cohomological form that William gave, with one extra step that I'm not gonna talk about. But sorry. So first we talk about elliptic complex. And William talked about the index, and at the beginning I gave the index of an elliptic operator, but what if you have an elliptic complex? What can you do? We have also a definition of the analytic index for this. So for an elliptic complex, L, which is a family of operators from L0, Li, from 0 to some n, 0 to I to n. So as follows. We're going to find its index, its analytic index. Is given by the index of L, is the sum, alternating sum of the dimensions, kernels, mod the image L. Okay, and we also have the topological index, which so it's the analytic index, and it's topological index. This one requires a lot more justification that I'm not going to give you, but just trust me, bro. Is right as T index, Tn of L is -1 to the n to n plus 1. Over to the integral over x of the return character of x. Then you pull back the symbol by the zero section. Here's the zero section. You wedge this with the tall class of tx, tm, transfer to the theorem over c. And you divide this by, I'll explain this in a second. Divide this by the order class of that. Okay. So I'll explain what these are. So first,
Actually,
here.
I have a question about the analytic one.
Yeah.
How much that I have like some infinite dimensional spaces and
Yeah. So that's a good question. Okay. Because I guess I never specified it to be elliptic over there. There's a chance I might have missed the condition there. You do have to restrict to the case where you can have only finite dimensional stuff, which I didn't really specify here.
Sorry, that you can have only finite?
No, that well, I don't think you want to consider the case where this quotient is infinite dimensional. So you have to consider, you have to restrict these operators to, so you can get finite dimensional.
Finite dimensional. Yeah.
Doesn't that work for if M is compact or something?
Not necessarily. I don't think so.
No.
I mean, it's kind of infinity stuff.
Yeah. Yeah. So that's. So let's add the condition that. Actually, okay. No. I think you still get the result. I think the procedure you're going to get is kind of similar to how you do for the case of you have just an elliptic operator.
Mm-hmm.
You can show that it's Fredholm, and then
what it means.
that means that the dimension of the kernel and the co-kernel are finite, and it has a closed image. So
That's some kind of story about choosing a metric or a manifold and like making E into Hermitian. Like, why space of section Hilbert to begin with or something like that?
yes. I don't think you. Okay, so I don't quite recall the proof of the way you do it originally, but I do think you have to fix some metrics.
Okay.
I don't know you're gonna get Hilbert, but you're probably gonna get Banach at the very least, and you can have some good enough stuff.
Yes, almost.
Yeah, there's some heavy analysis there. That's what I'm trying to get at, which I don't know on top of my head, unfortunately. But I think the same procedure you do for proving that elliptic implies Fredholm, and Fredholm gives you finite dimensionality
Yeah.
there. Same type of proof should give you here. That
Okay, cool.
this works. Okay, and going back to here. So, as here is a zero section of. Okay. So this is a zero section of my tangent bundle. So I guess first something. I guess I didn't specify, but you have to fix a metric. So here we work on the cotangent bundle, but fix a metric, identify the tangent bundle with the cotangent bundle, and then its logic call index becomes this. Okay, so you can consider the Tom class of the tangent bundle. And this is the zero section, so S of x is a 0 at x. The third character that Willem talked a bit about it in the last talk, but he's also going to cover characteristic classes, so I'll leave it to him to talk about these. Same for the Todd class, he defined that as well in, or he talked about it in the last seminar. And how can I divide by e to the m by the other class is that these things here are defined in terms of the Tom isomorphism, and this is multiplication by some class. And the idea is whenever, actually there's a much simpler explanation. The thing is, how you divide by this is you pull back to the some universal space, and this thing here is going to be, in the cohomology ring of that space is going to be invertible. So you can actually divide this. So you are going to the universal space B of SON, and there in the cohomology ring of that, this is invertible, so you can divide by it. We're going to complete this in a little bit, so.
Wells.
Yeah.
Wills, you want to say that again, Will?
Yeah, so the Euler class, the universal Euler class, is not invertible in the cohomology ring of that space because it has positive degree and there are no classes of negative degree. So it can't give you the unit. I think like what actually happens is that product you have on the top, you have to compute using like Chern-Weil theory that the Euler class actually divides that into unity. And so it makes sense to do that division because you can just, what do you call it, UFD, you can just pull it out because you can prove that it is a divisor of the numerator.
I have this strange feeling that I'm pretty sure I read somewhere that in the when I was preparing to talk that in the BSON you can divide by this in the cohomology ring of that. I have to check on that, but I'm pretty sure that is something that happened in my readings.
Right. Yeah, get back to me on that because
Yeah.
it's like the one over the way the class should have a negative cohomological degree.
Okay. Yeah, I'll get back to you on that, or I'll just look up my reference again at the end of this, and I'll let you know. Yeah. So whatever. Once you have this, we're gonna compare some examples where things work out nicely. Okay. So I'm not going to get into the full details of all these computations, but so for the talk class, I think I'll omit that computation because I don't want to go through the K-theory of that. But I can do some nice stuff anyways. Okay, so now we're in part 2. I did a quick review of things, which took me about an hour. But let's actually do some new stuff, some applications. And the first one is the Gauss-Bonnet theorem, which is a fairly simple one to do. And we already kind of have all the work for this one. So the theorem by Gauss-Bonnet. And actually, okay, so actually a specification on BSON, I want the manifold to be even dimensional. Because that's gonna happen here. Okay, to specify, this is invertible from what I remember in whenever n is even. If it's odd, then that thing is 0. The Euler characteristic is 0, so you cannot divide by it. But in the even case, apparently you can, from what I remember from my readings. So, and we're gonna use that here. So, but let x, be compact, orientable, a real manifold. Then you have the following famous formula. If I integrate the Euler class of the tangent bundle, is the same as the Euler characteristic of x. Which, if you don't recall, this thing here is the alternating sum of the dimension of the cohomology groups.
I also have to complain a bit about the Euler characteristic. I believe it isn't 0, but it is 2 torch. So when you're taking rational coefficients of certain 0, or you have like orientable manifold, am I right about that? I think so. I'm pretty sure it is like actually non-zero class in the universal case. But for an odd-dimensional manifold that's orientable, opposed and orientable, it's going to be 0 because the cohomology group where it would live doesn't have 2 torsion.
Okay. I don't usually work over. I usually work over R, so.
Oh shit! Yeah, sorry, I forgot.
Yeah, I usually work over field, so I don't really think about torsion too much. But I'll take your word for it.
Sorry.
Okay, so let's work through this theorem using the machinery we have. Okay. So, yes. Let's focus on the case where our x is even dimensional. Okay, let me erase this, and I'll keep that one there. So, proof, and we fix the dimension of x to be 2n. So, okay. Again, we fix a metric, fix a metric, so that the tangent bundle is isomorphic to the cotangent bundle. We just identify these two, and then we have our complex. So on the 0, I'm just going to write so sections from 0 to x. There's some pullback missing, but just for the sake of time, I'm not going to write everything. This is elliptic, as we talked before, and the index of B is going to be the alternating sum of the kernel mod the image, which is exactly the dimensions of the cohomology groups. So we have that. That's just by definition of what cohomology is. And now we look at the at the other side of the topological index. Okay. So again, for topological index, we have to tensor by C, and in that case, we kind of add the requirement that our metric be Hermitian, and so our complex we had before is going to change a little bit. We have it around. Yeah. So just because of the Hermitian case, because we have a Hermitian metric, it's going to change a little bit. So just by the fact that we need it to be conjugate linear, conjugate anti-linear, conjugate linear in one of the components. So the sequence induced by the symbols is going to be, I'm going to have some bunch of dots. I'm going to go to the P1 of the, here I'm going to keep the pullbacks. C, X, X, tensor C. And here I'm going to have I, C wedge, just because I need to be conjugate linear in one component, so I'm going to put the I there. Once I do this isomorphism, I'm going to go to B plus 1, pullback, CX. Okay, now you can compute the symbol. So, like, symbol of B. Okay, I guess, so, okay, the symbol I computed here is from the analysis side, but if you want to do the k-theoretic side, okay, so it's the same thing, just that you take care of, you keep track of the maps and where they're going from. So the way you would write this, my understanding using K-theory language, going to be as follows. So P from 0 to n, minus 1 to the P. Then you're going to have this, the class of the pullback, P, T, X, tensor C. This is in the completely supported K-theory, TX. And now what we're going to do, again, where's my index theorem? Okay, yeah. So when I'm here, I have my symbol. I want to pull it back by the 0 section. Then look at the churn character and compute that. So let's pull back by the 0 section. Where I'm at, I'm here. If I pull back by the 0 section, S star sigma D. If I do, the pullback is going to come S pullback here, but S pullback composed with pi pullback, that's just the identity map. So I just end up with minus 1 to the P, the class P, CX, C, and over P. And this thing here is exactly the Tom class. So now we're going to do, like I said, you have to go to a universal bundle here. So once you do that, you can use the splitting principle to assume that, to consider the case when Tx is a direct sum of plane bundles. With the rank EI equal to 2. And in this case, if you tensor by C, you're going to have that this is isomorphic, or this is equal K-theory of 1 plus L1 the conjugate, and you do this in times. Okay, where EI tensor C is isomorphic to Li plus Li. Okay. we good so far? Just use spin principle, filter by C, and you can think of each EI as a indirect sum of line bundles. So these are holomorphic line bundles, by the way. Now we can compute the Euler class of this. We have Tx. This is going to be the product of the Euler class of E1 En, which using this, again, you can identify EI as being one of these Li. This is the first Chern class of L1 Ln. If you want to review the first Chern class, I defined it 3 talks ago. And this is going to be the product. And the Chern classes are generators of the cohomology. So these are going to be the product of xi when I'm calling each one of these x1. I call this one. So I have this for the other class. Now let's look at this guy. If we do the Chern character of the Tongue class, well, I guess we can compute first simplify a little bit what this thing here is. By properties of the usual stuff, using the decomposition is going to be the same as Tongue class of L1 times the Tongue class of L1 conjugate, and so on for all the other ones. And this thing here is 1 minus L1, 1 minus L1 bar, 1 minus Ln, 1 minus Ln bar. Counting K theory, and taking the Chern character of this. Is going to be the product of the Chern character of 1 minus Li, 1 minus Ln bar, 1 to n. And now this, I don't know which one of you kind of saw this formula a little bit ago, but this is the same as 1 minus e to the xi, 1 minus xi. Okay. So if you want to kind of go through these computations, just go through the previous talks, how the Chern character is defined. This is homomorphism from K theory to homology, and you can compute that thing. Okay, and so this one I'm not going to compute it. This one I give a bit of computation, but for this other one I'm just going to give it to you what the Todd class is. This I'm just going to give you the formula right away. It's minus 1 to the n of product of xi over 1 minus e to the minus xi, and then the product of xi 1 minus e to the xi. Okay. Now we have all these formulas. We can put them in our Atiyah Singer index theorem in the cohomological form, and we have the following. So first, what the topological index is. Now that we have all these ingredients, this is going to be, again, let's rewrite the formula, minus 1 and plus 1 over 2 of the integral over x of Chern character pulled back with a symbol, which Todd of the tangent bundle, which you see, and the Euler class tangent bundle. So now putting our formulas together, this 1 to the n, this 1 plus 2, x. Here we're going to have a product of 1 minus e to xi, 1 minus e to the minus xi. Then we're going to have another product xi, 1 minus e to xi, and then another product xi, 1 minus e to the minus xi. this cancels with this cancels with this. One of these cancel with this, so we just end up with the order class and a -1. So we end up with this. I was not able to figure out how to get rid of this minus sign, but it has to be a way. I don't think this is always equal to 1. And n here is half the dimension of your manifold. So I wasn't able to get rid of that one. So I'm not sure if I made a mistake in my computation at some point, but I didn't have time to fix it. So I'll leave it up to you to try to figure out where did my sign go wrong. But worst case scenario, it's not so bad. Just up to a sign. Okay. So that's that. Now I'm going to give you a couple other, I'm not going to compute the other ones, but this is how you get the Gauss-Bonnet theorem. And you have other theorems that you also can get. So the other one I'm going to mention is Riemann-Roch, and then use that one to do an actual cool computation. Because these are fairly standard, but let's actually do a cool one to this. Okay.
The symbol that we used here, was this just from the other talk, or was it just like the symbols talk, or?
So it should be the same as from the other talk. I don't think Will computed a symbol for that sequence, but this is the symbol in the same sense of the other talks.
Okay.
So if you follow his talks and you just compute it, you should get this. Yeah, so this is the key theoretic. Sorry, because I was talking about the other type of symbol, but this is the key theoretic one. Okay.
Yeah.
So now let me write this theorem, which is Riemann-Roch, and let's use this. Riemann-Roch. I'm not sure how much I'll be able to get into this computation because there's a few things I have to define, but I think it's a cool application, and that's how generally you use, up to my knowledge, the Atiyah Singer index theorem. So we're going to let E be a holomorphic vector bundle of rank M, of complex rank M, over a compact Riemann surface. I usually assume my Riemann surfaces don't have boundary, so keep that in mind. Surface sigma of G is G. Then okay. Then we have this operator. So we have an operator. Let me just say it's elliptic. I have an elliptic operator, del bar, which goes from the sections of E to the sections, so I guess 0, 1 forms of values in E, right, like this, given by del bar, if I write it locally, Fi Si, where Si is a frame of my bundle, so N, then this thing here, this thing here is going to be the same as sum over I and J of D Fi D Z bar Zj Dzj bar tensor Si. Okay, so I have this operator. It's an elliptic operator. And the way you can show this is by computing its symbol, which I can give it to you right now if you want to compute it, but it's going to be also a wedge product by a non-zero section. By a non-zero section vector. But let me first state the theorem. So once you have this, then we have that. So then the index of del bar is given by M, which is the rank of your vector bundle, 1 minus the genus, and plus the integral over the Riemann surface of the first Turing class. Okay, so that's Riemann rock, and probably one of the most popular theorems in algebraic geometry and complex geometry. So the way it goes is kind of similar to how we did before. Have an operator, compute its its index is not so easy. It's not so hard to know what it is. It's going to be the kernel minus the co-kernel. But this part here is not the interesting one. The interesting part is here because you have these topological invariants. You have the genus, you have the rank, and you have the first Turing class. So it allows you to compute a lot of things from your vector bundle. You can compute degrees and all that stuff. So, but we're going to use it for something different. We're going to use it to compute, hopefully, if I have time, the dimension of the moduli space of stable maps with certain specifications. So first off, let me just mention that the symbol of del bar, and why you can see that it's an elliptic operator, is going to be equal to C 0,1 wedge, where I'm decomposing the tangent bundle of my Riemann surface. The cotangent bundle is the 1,0 part and the 0,1 part. And I'm just projecting down to the 0,1 part. So this 1,0 is the plus I eigenspace, and the 0,1 is the minus I eigenspace. Okay. So we have this, and one final definition before I start my procedure is if I have a complex vector bundle, again over my Riemann surface, sigma, and I have a PDO of order 1 between my vector bundle and 0,1 valued 0,1 form is valued in E, then we say that this is a generalized Cauchy-Riemann operator. If its symbol is like this for every S. Let's see. And once you have this, it's elliptic. This is invertible. Okay. Or it's an isomorphism. Okay, so we have the notion of a generalized Cauchy-Riemann operator. That is a Cauchy-Riemann operator. The kernel of this is really the things that are holomorphic. If you just look at the formula. So let's define. Let's consider kind of a problem in geometry and trying to figure out. Usually, these problems in geometry are defined by some PDEs, and so you have some differentiable operator, hopefully it's elliptic, and you can use the index theorem to compute the indices of these things. Okay, so what's our setup? So now here I'm going to change wheels a little bit and talk about moduli space of sticky curves. Okay. So we begin. Here I'm not going to give all the definitions, but if you want me to stop, I can give a definition. But we're going to start with a symplectic manifold. Very close. A symplectic manifold. Symplectic manifold. Of dimension 2n. Okay, once we have this, we're going to fix almost complex structure so that J, B, and omega tame almost complex structure. So what does this mean? Just quickly, it means that if I do omega, I do V, I do JV, the result is going to be bigger than 0 for every V. So usually if you say that it's compatible, usually assume this defines a metric that is for every V non-zero. V non-zero. Usually assume that it's compatible. You're going to have a metric, but you can relax this to just be omega tame. You're going to assume this is an almost complex structure of class CL. And we're going to define the following metric. So once you have an omega tame almost complex structure, you can still define a metric as follows. V1 half plus omega VJV plus omega, oops, sorry, GW. VW is going to be W omega W J. Okay, so it's going to be a Hermitian metric. Be the corresponding Hermitian metric. Okay. So, what is the space we want to consider? Usually, when you do, if you think back at like old results in mirror symmetry, what, for example, Candela, De La Osa, and others, and Eyal in the paper did, is they counted rational curves in Calabi-Yau threefolds. And so we want to find a way to count specific type of curves in our manifold. And the way we do it is as follows. So guess what type of curves we want to consider? They are the following. Let me find it properly. So we're going to consider the following space. MJ. Okay, first I guess we can define an operator as follows. So we define, once we have this setup, we can define these kind of Dolbeault operators, if you want to say, or Cauchy-Riemann operators, del bar, which depend on our almost complex structure for a section, for a map U. So if we define the bar of U, I'll say what U is in a second. It's going to be 1/2 PU plus J. J. Is going to be a 0-1 form, the pullback of the tangent bundle of my manifold, where U is a map from a Riemann surface into M. So, yeah, usually like this for now. And usually when U is in the kernel of this operator, you say that it's J-holomorphic. So they're called J-holomorphic curves. And if you kind of, the case where J is an integrable structure, then you can rewrite this to just be the equivalent of the Cauchy-Riemann equations in some general sense for this case. When this is equal to 0 on U. Okay. So, like I said, usually we say that the kernel of this operator are usually called, these are called J-holomorphic curves. Sometimes considering just holomorphic curves is not, it's too restrictive, so sometimes the rising condition should just be J-holomorphic. Okay. Once you have this, and here I guess also J is a map from a Riemann surface to M, and J is the complex structure of. Okay. All right. So this is where I'm going to start skipping a bunch of steps because they require a lot of analysis, but you can just take my word for a lot of these things. The reason why, because I'm not going to get too much into the details, but you want to restrict certain conditions about these curves. So once you have a symplectic manifold and you look at these curves, you have these notions of energy, which you can think of it as the integral over the surface of the pullback of. So what do I want to do? I can pull back my 2 form to here. It might be a volume form or not, depending on my u. But it's a 2 form, so it's going to go to a 2 form here. It might be a volume form, and I can integrate that. And sometimes you subtract something. If you have some Hamiltonian function on your symplectic manifold, you might do some correction terms. But the idea is you have this sort of notion of energy for these curves. And you want to restrict, so these are finite, they have finite energy or some sort of like finiteness condition. So that's how I'm going to motivate this following restriction of curves. But there's a lot more analysis going on around here. So we consider space, if you want to call it curve B, it's going to be a Banach manifold of all my holomorphic curves. So sigma is m such that u is J holomorphic, and also I want it to be in one of these Sobolev spaces, WKP. I want to be locally of this form, such that with I want k bigger than equal to 2, p bigger than 2, and usually I want to assume that L is sufficiently large to have the nice regularity conditions. Wait. I did not use any L's here, so. So we're going to consider this Banach manifold, and we're going to build a vector bundle over it and have a differential operator on it. So once I have this, I'm going to consider the following. So again, just remember our whole goal is to count holomorphic curves in our manifold. And again, our goal is to, in order to do this, we're going to need, so this is a space of holomorphic curves with some nice enough conditions. We're going to build a bundle over it in order to have a differential operator, and then look at the index of this operator, and hence be able to count these curves. So once we have this, we consider the following bundle. It's going to be a Banach bundle. Is a Banach bundle where the fibers are given as follows. So the fiber over some holomorphic curve mu is going to be W P minus 1 P, and it's going to be 0,1 form with value of the pullback. So I'm not really going to motivate as to why this is the right space to look at. Well, I guess, again, the operator you want to look at is some sort of curvature that comes from here. So once you have this thing, or once you have geometric, you have a Levi-Civita connection. And if you look at curves of this form and you look at the differential of this, it's going to be a map from the tangent bundle of sigma to the tangent bundle of m. And yeah, so if you kind of want to mix in both the holomorphic condition with some sort of differential condition. So the idea is you're going to define a connection where the covariant derivative is going to be the vertical part of the differential of du, if that makes sense, or the horizontal part, horizontal projection. Okay, so let me actually be precise about what's the thing you want to consider. Okay, so once you have this bundle, you have a section. You have a section given as follows. So, which is of class CL, given by S, this is going to be section S from V to E, given by S of U, it's going to be U, comma, like this. And you can show this is going to be a section of the following bundle. So now we have this. Okay. Let's leave it there for a second. Do I need this other operator? I don't need it. Okay. Let's leave it there for a second. I'm going to leave this one here. We're going to count the holomorphic curves. Now this one goes to the, this one here goes from 0, k to 0, k plus 1. But we also have another one from k, 0 to k plus 1, 0. Or k, p to k plus 1, p. So you have this other operator. So let's leave it here. Let's put a hold for a second. And we have this other operator, which kind of looks at the, this one looks at one direction. The other one's going to look at the other direction, at the other eigenspace. So we have another operator. E sub j, which on a curve U, on a map from a Riemann surface to M, is going to be the conjugate of this. So we're going to have a minus j, EU j. And now we can actually start mixing these two and look at the appropriate directions for that we want to consider. So go back here. I don't want to. I'm gonna erase this one.
I think I missed it. Is WKP like a sublet space?
Yeah,
Okay.
it's a sublet space. So you just use the WKP norm, and you have the local. Locally, it's going to look like some like Banach space, and you have these notions of you can use the usual norm locally. Okay, so we're going to let nabla be the Levi-Civita connection of my metric. And we're going to use this to define the following operator. So we're going to define a connection d sub u, where u is again a curve such that tu b goes to epsilon u on this is a connection on my Banach bundle, and the way that I wrote is going to be the vertical part. I'm not quite sure. I recall how there's actually an explanation as to why it's the vertical part of ds, but I cannot quite recall it at this time. I know it's in Magdaf Solomon's Bible, but I cannot quite recall the argument for this one. But you're going to take kind of a bit of a variation of what we did before. So we're going to take the covariant derivative of an element here. We're going to add the following j. So we have this kind of, in some way, like Cauchy, generalized Cauchy-Riemann equation for our connection, and we're going to look at how far away is it from the following. So I'm being a bit careful about how I want to write this without it being worrisome. Okay. Okay. So just in case the tangent space of this is going to be the WKB space k comma p of so it's going to be WKP sections of CM. Okay, so we have this sort of like modified Cauchy-Riemann equation you want to look at it at how far away it is from this. The intuition for that one is to see how okay, no. So this part here you can actually compute as some sort of like horizontal part, and you're trying to like take away the horizontal part from this thing here. That's why it's a vertical part. Okay, I remember. And this does require a bit of analysis. The idea is you define another nabla operator, and you can write that operator as some sum of two things, and one of those things is going to be this one, and it's going to be like horizontal and vertical, and you're just taking away the vertical part. The horizontal part. It's a bit of an annoying construction, but there is actual basis behind it, which is quite annoying. But I'm not going to get into that. Okay, I can provide references. It's not too hard. It's just a good bit of analysis you have to work through to properly describe these things.
Doesn't have the Levi-Civita connection on this spana thing, or is it on the base, like on
The nabla, or
yeah, the nabla?
The nabla here is the Levi-Civita connection of my symplectic manifold of M.
On M.
Yeah, and M I
What
have.
do you mean by nabla sub C? Because C is in.
Yes, you're right. Should be. Let me fix this real quick. It's in the pullback bundle. Okay, so it sees in the pullback bundle here. Okay, this is the thing. Yeah, so here's a little of a thing. You have to compose all of these by so this should be C compose U. So you take okay. Give me 1 second. I think this was fine. So here's the thing. Your X is in the pullback bundle of TM. So the elements of these things are going to be things of the form T, U, Z, M, right? And the idea is this C is, you're going to take kind of, so, okay. So if I look at, actually it's a section of that, so C is a section of sigma into Tn. So let me see how it is correctly written. It's just a bit annoying to specify. Okay, so if you give me a Z, it's going to be in T U Z M. So it's going to be a tangent vector in M, and that I can actually evaluate here. Does that make sense? Okay. Yep, that's what I mean. Yeah. It's, you can actually, the way it's written is really annoying the way they write it, because even if you look at this one here, if you look at this kind of stuff, even these formulas, they do require specific interpretation to have them, but it's just the way that people usually write them. So it's a bit annoying. You have to actually chase through it, but it does actually make sense once you go through it. Okay, are we okay? So, okay, now here's the, I'm gonna firstly skip these steps because I do have somewhere to be after this. And what you can do after once you have this is you can compute the index. And again, the way you do it is really using Riemann-Roch and a bit of the Atiyah Singer index theorem. You need a bit more work than Riemann-Roch, but Riemann-Roch is kind of the main tool to use to compute the index. But once you compute it, it requires a bit of work, but the index of du is going to be 2 times the first term class of the tangent bundle of your manifold wedge with, you're going to take the push forward of u and evaluate that at the fundamental class of C. So you take the fundamental class, you push it forward through U, and you add the dimension M, and then times 1 minus the genus. So you need to use Riemann rock plus some stuff to get this. But you see already one term of the Riemann rock. This one here requires a bit more justification, but it's not so hard to do once you can do this. And the other side, the analytic index, is really looking at the kernel of this. So you kind of get to see, you're gonna get to solve this kind of generalized Cauchy-Riemann equation. So this D sub U is actually a generalized Cauchy-Riemann operator, and that's why you have all these nice conditions. You have it's elliptic, so you can actually complete its index. And the idea is to solve these type of equations pretty specifically. If you look at the Floor equation, it's some sort of similar equation. You're just having the Cauchy-Riemann equations modified by a certain condition, and you also have some elliptic operator that you can just complete like this. So all these theories in the J-holomorphic curves, Gromov-Witten invariants, you really come from modifying the Cauchy-Riemann equations to get some other operator that kind of computes what you want it to compute, and then use index theorem to compute it. Okay, so once you have this allows us to compute the following. So this one requires, again, some more justification that I'm not going to go to. But if you look at the moduli space of genus 0 holomorphic curves that have values in A with respect to some complex structure, so just to be clear, these are holomorphic curves from a Riemann surface into M. So you want it to be U is J holomorphic. You want it that these things lie in a, you want that the push forward, so again, the push forward is going to be a map in homology, so it takes the fundamental class to some homology class, and I want to count those that lie in a specific homology class A. So if I fix A to be an H2 M, then I want the fundamental class to go to a specific homology class, and of course I need some condition, regularity condition, so I want this to be in WKP. So these are holomorphic curves that lie in A, WKP, and sigma has genus 0, so the genus 0 curve, genus 0. So if you have this, then doing a little bit of work, you have this operator inside that allows you to count these curves. So this operator here, you can actually write this as a, so this is actually mod equivalence. So you need it to be like isomorphic curves. But in a specific way, you need some diagram to commute. But once you have this, you can compute that this dimension and some open data set is really the index of du, which is exactly what I gave you before. So in the case that the genus 0, you only get 0 here, maybe 2 C1 Tm. You're going to have an A, so you're going to evaluate this at A, and then plus the dimension of that. So it requires a little bit more work, but it's not that much work. Once you get to this thing here, this is just a matter of rewriting what this equation actually means. You're going to find this actually this moduli space for in the case of genus 0. In the case of higher genus, you need to be a bit more careful. You need to have some correction terms because a lot more stuff happen in those spaces. So you have to add a couple of dimensions just to correct. But for the genus 0 case, which is the nicest one, the Riemann rock or this index formula actually gives you on the dot this moduli space dimension. So that's as much as I wanted to say for now. But again, the idea of computing the dimension of these moduli space is always the same. It's always look at your moduli space. Usually this comes from a physics problem. If you have these other invariants like Seiberg-Witten and instanton and stuff, also those are described in terms of PDEs, if I recall correctly. And just that moduli space, once you write it in terms of a PDE, you have a differential operator which you can compute the index for. And once you describe the space as kind of this as some quotient space of the kernel, then you can kind of end up computing these dimensions using this index theorem. So that's kind of a quick example, but there's of course more machinery behind it that you have to be careful for. Any questions? More detail that you want?
I had a question here. Do you need an integral somewhere here, like in the last few lines for the forms stuff?
Yeah. So this here actually you don't have a wedge product. So this thing here is actually it's an integral. So what I'm doing is I'm taking a cohomology class and pairing it with a homology class. So this really is an integral over the sigma.
Okay.
Yeah. So it would be like the integral over sigma of the pullback of by u of C1. Yeah. So here's an integral. I just wrote it like this because it's more standard the way you write it. But yeah.
And then like so
again, just to kind of like explain a bit more. So just again, once you look at these integrals over sigma, you're really looking at the energy of your curve. Usually you think these come from string theory, right? So you have these surfaces that are going in your space, and you're kind of looking at the energy of this I don't know how you call it. I don't know if it is, but I want to say like string moving through space.
world sheeter or whatever.
World sheeter, yeah. So you're looking at the energy of that, and you're trying to make sure that it has some nice conditions. So you want some finite energy condition and all this stuff. So this really is telling you that it depends on the energy of your sheet
And so like we were assuming before that we just had a regular like closed manifold and stuff, and then here you sort of did it for the Bana stuff, right? So then
Yeah.
Does it just everything carry over the exact same? Or?
There is a bit of care you need. So yeah, there is a bit of care that is needed. So a lot of the techniques do carry over. For this part here specifically, you have this generalized Riemann-Roch theorem, which works for Banach manifold up to a certain extent. There are some conditions you need to be a bit more careful for. But I'm pretty sure for this case here, you can I think for this here, you can do the same trick that you usually do in Morse theory, for example. If you look at the Morse homology of a space, there's two ways to kind of look at it. You can either look at it as points that lie in certain like descending curves. Like you have these flow lines that descend, and you can look at it as the space of points throughout these lines, or you can look at it as a set of lines, the moduli space of lines that kind of flow through these. And depending on which perspective you take, you have the same results, just that in one case you're going to have to use some Banach space technique, and in the other case you're going to have to use some more standard manifold theory techniques. I think you can play the same game for this case specifically. You can look, by just interpreting this in a different way, you can kind of think of this as really lying inside some finite dimensional stuff. But for a more general type of equations like this, you might not be able to play that game. For this one, I'm pretty sure you can, but there's a bit of trickery you have to go through. But in general, you have more general results that are similar. Yeah. But for this one, I'm pretty sure you can.
Actually, I have like a following question. But so naively, when I have a space whose tangent space at a point is some kind of a homology, I would assume that it came from some kind of Hamiltonian reduction type of construction.
Okay.
Where I had like and I had some kind of space. I took some kind of zero locus, maybe critical locus, and then I divided by some kind of rule.
Yeah.
And here I can see that I took like a critical sort of this zero set of some kind of equations,
yeah.
Maybe differential. Was there some point where I had to divide by some kind of isomorphisms to like sort of get like a kernel minus co-kernel?
Yeah. Okay, so you're asking, just make sure I understand. So here, since, okay. What you're asking is, since here you want to look at the zero set of this.
Yes, this is like I'm fixing some kind of sub-variety in this like big B.
Yeah.
Yeah, overall just did not understand the construction very well. Why was the tangent space the index of du and not just kernel?
Why is it tangent space? So this tangent space here.
Yeah.
Why is this?
Where is dimension of?
This is an infinite dimensional space.
Yes. Yes, and you saying that some. This is like but it's a vector space or like a Banach space. So its dimension is index of du, right?
No. So again, no.
Sorry, yes.
The dimension of the moduli space, you can make it to be the dimension of du in a nice enough case. On an open, there's a space, there's a subset where this is going to be surjective. There's some like stuff you need to worry about, but in some nice enough subset of this space here.
Yes, there is like a local coordinate on M is something like a flat sections of du, right?
Yes.
And why then I don't get just kernel of du and I get like kernel multiple kernel?
Oh, that's a good question. Okay, give me 1 second. Give me 1 little second. So there is yeah. So this is how the proof goes for this one. The thing is that for nice enough u's, this thing here is going to be surjective. So the co-kernel is just 0.
Oh, I see. Okay.
Yeah, and usually that's kind of what you want. You don't want to compute both kernel and co-kernel. Usually you want to stick your space with that
Oh,
co-kernel.
so it's just kernel is 0.
Yeah.
That makes sense.
So you do end up with a kernel only.
Ah, that's a problem. It's about my curves, not kernel tomorrow.
It's a bit of a proof, but that's usually how these things go. Like Devin Solomon has like I think it's like 900-page book on this theory, so it's quite the work.